Okay, so we are going to look at a problem of a car along a ramp. So this car is traveling down the ramp of 6 degrees with respect to the horizontal. And we want to look at what the maximum acceleration of this car is just while the tires are on the verge of rotating. So it's kind of sliding down this ramp, but we're going to look at the static friction acting on those tires just at the verge of them starting to roll, so no rolling friction, under 3 conditions: dry, wet, pavement, and ice. So we can assume the anti-lock brakes are working here. All right, so the first thing we have to do is determine the coefficients, which I've presented here, but what are the 2 interacting objects? Well, we have the rubber tires and the pavement. And so these are the coefficient of friction that we look up for concrete and rubber. Now, it tells us in the problem that for the case of ice, imagine it's like a shoe. So the bottom of a shoe, and that's the coefficient of static friction for the bottom of a shoe and ice. All right, so we look those values up, and we assess this as a force analysis problem. We want to keep in mind we're dealing, like I said, with static friction. We're at that maximum point, just on the verge of slipping. And so we want to keep in mind that the static frictional force in this case is equal to the coefficient of static friction times the normal force. And this is when we are at maximum static friction. So we're going to utilize that relationship in the problem today. All right. So this is a force analysis. We want to identify, of course, what is our object of interest, and that is the car. I'm going to identify down the ramp as our positive direction. So what are the forces acting on this car? Well, we know there's the force of gravity. So we have the force of gravity acting on the car. It has a mass, and that's going to be between the car and the earth. We also know that there is a normal force. The car is interacting with the road, so that's between the car and the road. And of course, there is the force of friction. And it's static friction. We've talked about that Y already, and that's between the car and the road. So those are our 3 forces acting on the object. So let's draw a free body diagram of the car. Regardless of which condition I'm looking at, these remain the 3 forces acting on the object. So we can set the problem up as a general problem and then use the different coefficients for each one of our conditions. So the force of gravity, how does that act on the car? Well, we know it acts earth vertical. So here's our force of gravity, and just as a reminder, that's equal to mg. What about the normal force? Well, that acts perpendicular to the surface. So that kind of points up and to the right because the surface is at that angle of 6 degrees. And what about the frictional force? Well, it's preventing the car's motion, which is down the ramp. And so the frictional force will be parallel to the ramp and in the opposite direction. So that's our static frictional force. It's preventing the rotation of the tires as they would go down the ramp. So here are our 4 forces. Excuse me, there's only 3. Here are 3 forces. So we're going to break them up into their horizontal and vertical components. Now, we want to look at the components in a single dimension. Why? Well, if we have the dimension rotated, if we rotate our coordinate system, then the motion and the change in motion is along the ramp horizontally, what I'm going to call horizontal prime. And there's no change in motion vertically, which I'm going to call vertical prime. So if we rotate our coordinate system to align with the direction of the motion or intended motion, then the orthogonal direction has no net force. And that's going to be a very helpful mathematical tool for us as we analyze this problem. So we're going to rotate that coordinate system. When we do that, the force of gravity actually has a component in the direction of the motion, parallel to the ramp, and perpendicular to the ramp. Parallel to the ramp, that component is the force of gravity, or mg, times the sine of the angle. It's positive because I've defined the positive direction as down the ramp. Vertically, well, that's in the downward direction as I've defined it, minus mg times the cosine of the angle. All right, so what two components are we looking at? We know that this is our 6 degrees, right? So the ramp causes this to be 6 degrees, so this is our angle. Down the ramp is opposite, so the sine. Along that perpendicular direction is adjacent to that angle, so it's the cosine. That's where I get that sine and cosine. I've been explicit about my directions based on how I've defined the positive direction, both horizontally in my horizontal prime and vertically, so in my rotated coordinate system. Force number 2, the normal force. Well, that is indeed along this rotated coordinate system in the positive vertical prime direction relative to that coordinate system I've drawn. And force number 4 is also along the coordinate system. It's up the ramp in the direction I've defined as negative. All right, so the sum of the forces in the vertical direction is the mass times the vertical acceleration. The sum of the forces in the horizontal direction is the mass times the horizontal acceleration. Now again, these are horizontal prime and vertical prime, along the ramp and perpendicular to the ramp. Well, there's no change in motion perpendicular to the ramp, so the sum of these forces in the vertical direction are 0. We know that n minus mg cosine of theta is equal to 0. That tells us that n is equal to mg times the cosine of theta. What about horizontally? Well, horizontally, mg times the sine of theta minus the frictional force is equal to the mass times the horizontal acceleration. And that's what I want to know. What is the horizontal acceleration? Well, I'm going to remember that the maximum static friction is the coefficient of static friction times n. I'm going to use that in my relationship. So I have mg times the sine of theta minus mu sub s n is equal to m times the horizontal component. Again, I'm interested in that horizontal acceleration. But my normal force is mg times the cosine of theta. So I'm going to bring that in here, and I end up with mg times the sine of theta minus the coefficient of static friction, mg times the cosine of theta. So this is n. Oops, we're off screen there. I'm setting that a little bit higher so you can see it on the screen. This is my n, kind of tiny there. That's the n, is going to equal mass times the horizontal acceleration. So we see that there's an m in every one of these terms. I can divide all sides by n, both sides by m, as in Michael, m, the mass. When I do that, all of these m's cancel out. So the problem never gave us the mass of the car, but it's irrelevant. It's irrespective, this behavior of the mass of the car. So I'm going to rewrite this up here where I have a little bit more room. We're going to say g times the sine of theta minus the coefficient of static friction times g times the cosine of theta is equal to my horizontal acceleration. And so all I have to do from here on out for parts A, 1, 2, and 3 is to use the appropriate coefficient of static friction. So for part A on dry concrete, this term, mu sub s times g times the cosine of theta, is equal to 9.74. 9.74. And when I plug that into my relationship, I find that horizontal acceleration to be negative 8.72 meters per second squared. What does this negative tells me? It tells me that acceleration is up the ramp. That acceleration is up the ramp. So the car is going to slow down. It's in the direction opposite the motion. Excellent. What about for wet cement? Well, even on wet cement, we find that mu sub s g times the cosine of theta is equal to 6.82. And when I plug that into my relationship, we find the acceleration to be negative 5.8 meters per second squared. So the acceleration is still up the ramp, but it's not as big. And so on wet pavement, we do not get as large of a slowing down as the car moves down that ramp. And that's to be expected. We don't slow down as fast on wet pavement. What about on ice? Well, on ice we find that mu sub s g times the cosine of theta, using our coefficient of static friction for ice, is equal to 0.97. When we use that into our relationship, our acceleration is equal to a positive 0.05 meters per second squared. That's down the ramp. That means on ice, the car does not slow down. It continues to speed up down the ramp. So the direction of the acceleration gives us an indication of what's happening to that car as it's going down the ramp. When the acceleration is in the direction opposite the ramp, when the static frictional force is large enough, the car will indeed slow down as it goes down the ramp. Motion is down the ramp, acceleration is opposite that motion, the car slows down. Same with wet, which is good, because we need to slow down as we go down the ramp, but we have a problem on ice. So we always have to drive carefully on ice, because on ice, that acceleration is still going to be down the ramp, which means the car is going to be speeding up. Motion down the ramp, car down, acceleration down the ramp as it goes down that ramp. All right. Process is the same for all three conditions, recognizing those forces, recognizing we might want to rotate that axis so that we're looking at motion along the ramp. Once we do that, we find that that mass is irrelevant. In this case, it shows up in every term, and therefore we can cross it out of each term. We end up with this equation that works for all conditions, and then we use our coefficient for each condition to get this term in the equation and solve for the acceleration under each condition. All right, good job.